Hello friends, my name is D. Raju. I am working as lecturer in chemistry at Government College Autonomous, Anantapur. In this video, we will discuss about ligand substitution reactions as part of our inorganic chemistry study. First, if we see the learning objectives of this topic are to know about the concept of ligand substitution reactions, types of ligand substitution reactions in metal complexes, and the mechanism of SN1 and SN2 reactions in octahedral complexes, and also we will come to know about ligand substitution reactions in square planar complexes. First, if we see the introduction of this topic, here in these reactions, substitution of a ligand present in a metal complex with another ligand. That means one of the ligand present in a metal complex is replaced by another ligand. If we see the example here, this is the complex MLNX. Here M is the metal, Ln are n number of ligands, and one of the ligand is X. So if this complex reacts with another ligand Y, then this Y going to replace this X from this initial complex. So therefore the X present in this complex is replaced by Y and X is coming out. So therefore we can say that X is the leaving ligand here and Y is the entering ligand here. And generally these reactions are examples for nucleophilic substitution reactions. That means, as we know, metal is a positive centered body and the ligands are their negative charges. So here the entity which is having negative charge, that is nucleophile, is substituted by another nucleophile Y. So therefore we can say that these reactions are nucleophilic substitution reactions. And depending on the chemical kinetics, that means what is the rate of the reaction, how fast the reaction is going to take place. So depending on the rate of the reaction, that means chemical kinetics, these reactions are classified into two types. One is SN1 reactions, another one is SN2 reactions. So if we see again we can see here, so there is a complex ML5X, that means here the coordination number of this metal is 6, 5 L ligands are there, 1 X ligand is there. So therefore this is an octahedral complex. We are taking this as an example for a octahedral complex ML5X, and we are making it to react with Y. And here Y is going to replace this X here. So therefore we are getting ML5Y. That means in place of X we are getting Y in this substitution reaction and X is coming out of this complex. And this mechanism which is happening in octahedral complexes may proceed in two ways, that is SN1 and SN2. So S stands for substitution, N stands for nucleophilic, and 1 stands for unimolecular. Here 2 stands for bimolecular. So we will going to learn about them. What are these unimolecular and bimolecular? So these SN1 reactions, as we have said, these are the nucleophilic substitution reactions, unimolecular, and the mechanism in which these reactions takes place is called as dissociative mechanism. So here in these SN1 reactions, the rate depends only on the concentration of the metal complex, but not on the concentration of the incoming ligand or entering ligand. So we have seen here we are having two reactants. One is the metal complex, another one is the entering ligand. Here in these SN1 reactions, the rate of the reaction, the velocity of the reaction depends only on the concentration of the metal complex, but not on the concentration of the Y. Therefore, we call them as unimolecular nucleophilic substitution reactions. So here the rate is proportional to concentration of the metal complex only. Therefore, this rate can be written as rate is equal to K into complex concentration to the power 1. So this 1 indicates it is a first order reaction. Therefore, we are calling it as unimolecular reaction. If we see the mechanism of these SN1 reactions, these reactions takes place in two steps. And as we have already said, this is the example for dissociative mechanism. And in the step 1, let us suppose we will take a octahedral complex. This Ml5X is an octahedral complex with coordination number 6. As we know, octahedral complexes will have coordination number 6. And in the first step, this complex will involve in the reaction, and this step is a slow step. So whenever we are calling a step as a slow step, that can be referred as rate determining step in chemical kinetics. That means the speed of the reaction depends on this step. That means the speed of the reaction depends on the concentration of the reactants present in the slow step. So in the first step, this complex with Ml5X configuration will lose one of the ligand X. So therefore it becomes as Ml5. That means here the coordination number 6 is becoming coordination number 5, and this Ml5 complex is a reaction intermediate, and generally these reaction intermediates are unstable. And this complex Ml5 will have a geometry of trigonal bipyramidal or square pyramidal. So this is the first step. In this first step, complex is losing one of the ligand and forming a unstable reaction intermediate which is having trigonal bipyramidal or square pyramidal structure. In step 2, this Ml5 will undergo a fast reaction. That means it undergo a combination reaction with another ligand Y and will convert into Ml5Y, again with coordination number 6 with octahedral geometry. So in this step, the intermediate is reacting with Y in a fast manner and giving the product Ml5Y. So initially we have taken Ml5X complex and finally we got Ml5Y complex. Here in place of X, this Y got substituted. So therefore we can say that it is a nucleophilic substitution reaction. So if you see the mechanism here with an example, so initially we have seen this complex Ml5X, and this is the Ml5X complex which is octahedral shape. As we know, this shape is the octahedral shape. In the first step, that is the slow step, it loses X, so therefore we have written as minus X. And after losing X, this complex is becoming like a trigonal bipyramidal intermediate. So here M is the metal and 1, 2, 3, 4, 5 ligands are surrounding it. Therefore, this complex is having Ml5 composition, and this is a trigonal bipyramidal moiety. And as we know, in the second step, that is the first step, another ligand, external ligand or entering ligand Y is going to react with this intermediate in a fast way to give the Ml5Y complex. So here in place of this X, Y got replaced. So therefore, this reaction can be taken as a nucleophilic substitution reaction because the entering ligand is a nucleophile and the leaving ligand is a nucleophile, and this reaction is proceeding via a trigonal bipyramidal intermediate. As we have seen, this reaction may take place by the formation of another intermediate called as square pyramidal intermediate. So here this shape of this moiety is the square pyramidal because these 4 ligands are arranged like a square manner and this ligand is like a pyramid for it. So therefore we can call it as square pyramidal structured moiety, which is the intermediate. And again this moiety will undergo a fast combination reaction with Y to give Ml5Y complex. In this way, through these 2 types of intermediates, we are getting the final product in SN1 reactions. So see, here why we are calling it as dissociative? Because initially the complex is undergoing dissociation in the slow step. As we have seen, rate determination step or slow step is the important step in the chemical kinetics. So therefore in the slow step, the original complex, reactant complex is undergoing dissociation. Therefore we are calling it as dissociative mechanism. Next, if we see the SN2 reactions. And contrary to SN1 reactions, the mechanism of these reactions can be told as associative mechanism. So here we will see, we have already seen N is the nucleophilic, S is the substitution, and 2 is the bimolecular. So we are going to know about this reaction. So here the rate of the reaction in SN2 reactions depends on the concentration of the metal complex and incoming ligand. That means here the rate of the reaction, the velocity of the reaction depends on metal complex concentration as well as entering ligand concentration. So both the complex and entering ligand are involved in the mechanism, a rate determination step. Therefore, we are calling it as bimolecular mechanism. And so here we can illustrate this with an example here. So again, ML5X is a complex and it is reacting with Y, and it is giving a product ML5Y, and X is get replaced by Y in the substitution reaction. Here, as we have discussed, the rate is proportional to the concentration of the metal complex and also the concentration of the incoming ligand. So both the concentration terms are there. They are having power 1 and power 1. So therefore, we call it as 1 plus 1 equal to 2 second order reaction. That's why we have written 2 here. That's why we are saying that it is a bimolecular mechanism. And this is also, that means SN2 reactions are also takes place in 2 steps. In the step 1, the coordination number 6 octahedral complex ML5X reacts with Y in a slow step. That means in slow step, both the complex and entering ligand both are involved here. Therefore, we are calling it as bimolecular. Whereas in SN1, only metal complex is undergoing dissociation. Therefore, we are calling it as unimolecular. Therefore, we are calling it as dissociative. Whereas here, the metal complex is associating with the entering ligand. Therefore, we are calling it as associative mechanism. And also, both the concentration terms are involved in the rate equation of this SN2 reactions. Therefore, we are calling it as 2, that means bimolecular mechanism. So, in the first step, metal complex reacts with Y and gives a coordination number 7, pentagonal bipyramidal or octahedral wedge-shaped unstable intermediate, which is ML5XY. Here, the number of ligands around metal are 7. 5 L's are there, 1 X is there, 1 Y is there. Therefore, the total coordination number is 7. And this moiety will have a shape of pentagonal bipyramidal or octahedral wedge shape, and this is a unstable intermediate. In the step 2, this unstable intermediate, which is having PGBP or octahedral wedge structure, will undergo dissociation or will lose X to give ML5Y, which is the desired product in our reaction. And this ML5Y is having coordination number 6, and again it is octahedral complex. So in this way, in SN2 reactions, 2-step process will take place. And overall, if we write SN2 reaction, initially there is a coordination number 6 octahedral complex is there, ML5X. It is undergoing association with Y in a slow step, and it is giving a coordination number 7 unstable intermediate, and this intermediate is losing X to give the final product ML5Y. This is having coordination number 6, and this is octahedral shape. And if you see the mechanism, so we will take ML5X complex here, octahedral complex. In a slow step, Y is reacting with this complex. So therefore, we are getting a pentagonal bipyramidal intermediate, which is unstable. And here we can see the 7 ligands around the metal. 1, 2, 3, 4, 5 L's are there. 1 X is there. 1 Y is there. And these X and L are acting like pyramids. Therefore, we are calling it as bipyramid. And there are 1, 2, 3, 4, 5 ligands are in one plane. So therefore, it's pentagonal. It's just like a pentagonal bipyramidal structure. And this pentagonal bipyramidal structure losing X to give the octahedral complex ML5Y. Only difference between ML5X and ML5Y is in place of X, Y got replaced here. This is one type of mechanism. In another way, we can say that this ML5X again associate with X to give a octahedral wedge shape. So this is the octahedral wedge shaped intermediate. So octahedral, and there is a wedge type of thing. So octahedral wedge shaped intermediate we are getting, and this one is losing X to give the product ML5Y. In this way, the SN2 or associative mechanism takes place. And again, see, next we will go to the Ligand substitution reactions in square planar complexes. So as we know, generally the metal ions with D8 configuration, they form the square planar complexes. And for square planar complexes, the coordination number is 4. That means around the metal there will be 4 ligands arranged in square manner in a planar way. So example, if we take the metals ions or metal ions like platinum plus 2, palladium 2 or nickel 2, gold 3, rhodium 1, iridium 1, and these ions form the square planar complexes with coordination number 4. So here in these reactions, one of the ligands in the square planar complex is replaced by another ligand which has stronger nucleophilicity. That means, so we will take a square planar complex. In this square planar complex, one of the ligand is replaced by one outside ligand or entering ligand to give the product. And in these reactions, sometimes the rate of the reaction depends on the coordinating ability of the solvent also. That means we will take the reactants in a particular solvent like water or ammonia, etc. And this rate of the reaction of the substitution reactions depends on the coordinating ability of the solvent. That means it depends on the nature of the solvent also. So if we take the example, we are taking a platinum complex here, platinum plus 2 complex. And around this platinum, there are 3 ammonia molecules, ammonia ligands are there, and 1 chloro ligand is there. And this complex is reacting with water, and water is the entering ligand here. So in place of chloro, the water is getting replaced here, and chloro is coming out as Cl minus. So therefore, this reaction can be taken as an example for a substitution reaction in square planar complex, because one of the ligand chloro is getting replaced by another ligand water here. So these reactions, substitution reactions, may occur in 2 different ways, and one way is called as solvent path and the second way is called as displacement path, and we will see what are those. In solvent path, substitution reaction or substitution of one of the ligands through the solvent molecule. That means initially in the first step, the solvent molecule will be involved in the reaction. See, in the first step, let us suppose we will take a platinum complex, platinum triamine chloro complex, and it is reacting with the water, and this water here is a solvent molecule. So the solvent is reacting with the complex in a slow step, and this is a reversible step. That means both forward and backward reactions takes place. And in place of this chloro, water is getting replaced in the first step. So solvent is involved in the first step. In the second step, what happens? This solvated complex or this water substituted complex again reacts with another entering ligand Y minus to produce the desired complex PT NH3 thrice Y. That means in place of chloro, there is another ligand, entering ligand got replaced here, and water will be released as it is like a solvent molecule. So why we are calling this as a solvent path? Because in the slow step or rate determination step, solvent is involved here. Through the solvent molecule, the substitution is taking place. Initially, the solvent is replacing the leaving ligand, and in later stage, the entering ligand is replacing the solvent molecule. So therefore, we can call it as a solvent path reaction. And in displacement path, and this displacement path involves SN2 mechanism like we have seen in octahedral complexes, and here also the trigonal bipyramidal or square pyramidal intermediate will be formed here. Then retention of configuration in the products. That means products will have the same configuration like the reactants. And if we take the example, so PT NH3 thrice Cl, this is the complex, original complex, and it is reacting with entering ligand Y minus, and this is a slow step. So in the slow step, both entering ligand and the square planar complex both are involved here. Therefore, we can say that it is processing by SN2 mechanism, and both these reactants react to give this intermediate, and this intermediate will have a trigonal bipyramidal shape or square pyramidal shape, and this complex or this moiety will undergo a fast dissociation of the Cl to produce our complex, desired complex, platinum NH3 thrice Y plus, and Cl is coming out. So in this way, we are calling it as displacement path. Why? Because directly the Y minus entering ligand is replacing the existing ligand Cl. So therefore, we are calling it as displacement path. So in this way, in this solvent path and displacement path, the square planar complexes will undergo ligand substitution reactions. So friends, these are our topics. So far we have discussed about what are the substitution reactions, what are SN1 reactions, what are SN2 reactions, how the ligand substitution reactions are taking place in octahedral complexes, why we are calling the reactions SN1 reactions as they are processing by dissociative mechanism, why SN2 reactions are proceeding by associative mechanism, and what are the solvent path reactions, displacement path reactions in the ligand substitution reactions of square planar complexes. So these are the topics we have covered, and these are some of the reference books where you will find more information about these topics. So thank you for watching.